Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Dear students, I am Professor Dr. Zora Nazir Kiani from Physics Department of Lahore College for Women, University Lahore, with your MS coursework Semiconductor Electronic Devices. You know that we are discussing the chapter Integrated Circuits, and today we will discuss the charge transfer device, the basic CCD. CCD means charge coupled device, and then the applications of CCDs. So actually what is going to happen in CCD, this is the charge transfer device in which light is converted into charge. As you can see here, light is falling on the semiconductor material. Here we have got the substrate, and on the top of the substrate n-doped silicon is deposited, and then on the top there is silicon dioxide layer. So when the light fall on the device, it changes into the charge. That is, here you can see separation of positive and negative charges is taking place. Now here we have applied minus 10 volt, here minus 5 volt is applied to the electrode. So negative biasing leads to the increased capture of holes under pixel electrodes, because here n-doped silicon dioxide, so negative biasing will produce the more capture of hole. Then there will be creation of potential well. Photon ejects electron and device collects and stores charges. There are 10 raised to power 5 10 power 16 charges per pixel. This is configured as CID or CCD. This CCD or charged coupled device is one of the most interesting and broadly useful integrated device. The CCD is a part of broader class of structures known generally as charge transfer devices. These are dynamic devices that move charge along a predetermined path under the control of clock pulses. These devices find application in memories, various logic functions, signal processing, and imaging. In this lecture, we lay the groundwork for understanding these devices, but their present forms and variety of application must found in the literature available on the internet or in any books published nowadays. But I will discuss application here as well, which I have found in the nearmost literature. So you must understand this, that the basis of CCD is the dynamic storage and withdrawal of charge in series of MOS transistors. Thus, we must begin by extending the MOS transistor, which we have discussed in the chapter number 6 about field effect transistor. Now here you can see a figure which shows a MOS capacitor on a p-type substrate with a large positive gate pulse applied. A depletion region exists under the gate, and the surface potential increases considerably under the gate electrode. In effect, the surface potential forms a potential well which can be exploited for the store of the charges. Now here you can see a MOS transistor with positive gate pulse here. Here is the depletion region, which marked here this depletion region, and a potential well at the interface, which is partially filled by electrons corresponding to the surface charge as shown as surface charge, which are shown in figure A. The potential well should not be confused with the depletion region, which extends into bulk of the semiconductor. The depth of the well is measured in the electrostatic potential, not distance. Electron sodium potential well are in fact located very near to the semiconductor surface. If the positive gate bias has been applied for sufficiently long time, electron accumulate at the surface and the steady state inversion condition is established. The source of these carriers is the thermal generation of electrons at or near on the surface. In effect, the inversion charge tells us the capacity of the well for stored charge. The time required to fill the well thermally is called the thermal relaxation time, and it depends on the quality of the semiconductor material and its interface with the insulator. For good materials, the thermal relaxation time can be much longer than the charge storage times involved in CCD operation. If instead of steady state bias, we apply a positive pulse to the MOS gate electrode, a deep potential well is first created. Before inversion has occurred by thermal generation, the depletion width is greater than it would be at equilibrium. This transit condition is sometimes called deep depletion. If we can inject electron into a potential well, electrically or optically, they will be stored there. The storage is temporary. However, because we must move the electrons out to another storage location before the thermal generation becomes appreciable. What is needed here? A simple method for allowing charge to flow from one potential well to an adjacent one quickly and without losing much charge in this process. If this is accomplished, we can inject, move and collect packets of charge dynamically to the variety of electronic functions. Now we will study the basics of CCD. The original CCD structure proposed in 1969 by Boyle and Smith of Bell Laboratory consisted of a series of metal electrodes forming an array of MOS capacitors as shown in this figure. At time t1, this here is the time t1. And here is the array of the MOS capacitors connected, and here is the time t1. So at time t1, the potential well exists under each G1 electrode, and we assume that this well contains a packet of electrons. Here it contains packets of electrons from a previous operation. At time 2, a potential is applied across the adjacent electrode G2 and the charge equally across the common G1 and G2. Here you can see initially we were having here the potential well along the G1 only. Now it extends to G1 and G1 too as well. It is easy to visualize this process by thinking of the mobile charge in similarity with a fluid which flows to equalize its level in expanding container. This fluid model continues at T3 when V1 is reduced, thus decreasing the potential well under G1. Now charge flows into G2 well, and this process is completed at T4 when V1 is equal to 0. Here you can see that when V1 is reduced, then this charge moves from G1 to G2. Here you have seen that it is moving from gate G1 to G2, and when the V1 is 0, then it totally is collected at the in the well across the gate G2. By this process, the packet of charge has been moved from under G1 to G2. As the procedure continued, the charge is next passed to G3 position and continues down the line as the time proceeds. In this way, charge can be injected using an input diode, transported down the line and detected at the other end. Now here we have got G1, G2, G3. Similarly, G1, G2, G3. And so you have seen that in this way our charge just move from starting from G1 to the other side. Now how we can improve the basic structure of CCD? This is the structure and how the improvement can be brought in this basic structure. There are several problems which arise in the implementation of the CCD structure, which is now discussed. For example, the separation between electrode must be very small to allow the coupling between the wells. An improvement can be made by using an overlapping gate structure, which is shown in our next figure. I will move to the next figure. Before moving to next figure, you can see here V1 was positive when we got charge accumulation in the potential when at gate G1, and when both potential are equal, that is V1, V2 are positively supplied, then this is equally distributed, and when V1 was reduced, then it moved to the G2 and partially remain in G1, and when your V1 is 0 and V2 is positive, then all is moved to the gate G2. Now this is the same picture which I have discussed in the previous figure. Now I will discuss with you the improvement in basic structure by considering this figure. Here you can see that an this is the overlapping gate CC structure. One set of electrode is polycrystalline silicon, and the overlapping gates are aluminium in this case, and silicon dioxide separates the nearby electrodes. Here you can see that we have got p-type silicon here, and then we have got here polycrystalline silicon here at the gate, and then we have got the overlapping gates are aluminium in this case. Here we have placed aluminium, and silicon dioxide is separating this substrate from the gates. So you must have understood from this figure that an improvement we can be made by using an overlapping gate structure, and this can be done with polysilicon electrode separated by silicon dioxide layer, or with the alternating polysilicon and metal electrodes, that one polysilicon, then metal electrode, then polysilicon, then metal electrode. One of the problems inherent to charge transfer process is that some charge is inverted last during the many transfers along the CCD. If charges are stored at the silicon dioxide interface, surface states trap a certain amount of charges. Thus, if the zero logic condition is an empty well, the leading edge of a train of pulses is degraded by the loss of charge required in filling the trap which were empty in the zero condition. One way of improving this situation is to provide enough bias in the zero condition. One way of improving this situation is to provide enough bias in the zero state to accommodate the interface and the bulk traps. This procedure is referred to as using a fat zero. Even with use of fat zeros, the signal is degraded after a number of transfers by inherent inefficiencies in the transfer process. Now, the transfer efficiency can be improved by moving the charge transfer layer below the semiconductor insulator surface. This can be accomplished by using ion implantation or epitaxial growth to create a layer of opposite type than the substrate. This shifts the maximum potential under each electrode into the semiconductor bulk, thus avoiding the semiconductor insulator interface. This device is referred as buried channel CCD. Now the previous figure which we have seen the move of the charge from one potential well under one gate to other potential well gate, that is only one example of variety of CCD structures. But if I move to my next slide, here two-phase CCD with an extra potential well in under the right half of each electrode by donor implantation. This is another way of creating increasing efficiency or improvement, a step to improve the basic structure of CCD. This figure illustrates one method for achieving a two-phase system in which voltage are sequentially applied to alternating gate electrodes from two lines. Alternating gate electrodes from two lines. A two-level polysilicon gate structure is used in which the gate electrodes overlap and a donor implant near the silicon surface creates a built-in well under half of each electrode. Okay, girls. A two-level polysilicon gate structure is used in which the gate electrodes overlap and a donor implant near the silicon surface create a built-in potential under half of each electrode. When both gates are turned off, then the potential well exists only under the implanted region, and charge can be stored in any of these wells. With electrode G2 pulled positively, the charge packet shown here in B. Charge pockets are shown here in figure B is transferred to the deepest well under G2, which is its implanted region as C indicates, like here. Then with both gates off, the well appear as in B again. When both gate are off, then it will appear as B in again, except that the charge is now under the G2 electrode. The next step in the transfer process obviously to pulse G1 positively so that the charge move to the implanted region under the G1 electrode to the right here, so that it can move here toward the right. Other improvements to basic structure are important in various applications. These include channel stops or other methods for achieving lateral confinement for the stored charge regeneration. Regeneration points must be included in the array to refresh the signal after it has been degraded. So we have discussed three structures of your CCD. Here you can see the silicon is here, that is a substrate, and then you have just a insulated layer, silicon dioxide. Then you implant these ions which are donors, and then you can see here polysilicon here, which is shown by this black, and here you can see the gate G2 is connected with metal electrode, then G1, then G2 and G1, and so these are the three structures. This is the final structure which we have discussed so far. Now there are certain applications of CCDs. CCDs are used number of ways, including signal processing functions such as delay, filtering and multiplexing several signals. And other interesting application of CCD is an imaging for astronomy or in solid state TV cameras, in which an array of photosensors is used to form charge packets proportional to light intensity, and these packets are shifted to detector point for readout. There are numerous ways of accomplishing this in CCDs, including the linear array line scanner, in which the second dimension is obtained by moving the scanner relative to the image. Alternatively, an area image sensor can be made which scans the image electronically in both dimensions. The latter device can be used as an alternative to electron beam addressed television imaging tube. So, how is the integrated circuit technology is bringing revolution in your electronic devices? Not only their size is reduced, but also their efficiency is also increased. So girls, I will assign you an assignment in your Google class, and you have to write about the applications of this CCD device which is used to transfer the charge. That is, you have to write the applications of charge coupled device which are using nowadays at the industry level, even at the home level as well. Thanks for your concentration.